So what I just spoke about is even much more emphasized in the area of my interest in the cloud computing, that is high performance computing in the cloud. While networking, especially photonics, will be enabler for overall cloud, it's absolutely essential for high performance computing in the cloud. It's possible to accomplish without it, but the amount of applications that could be covered is very limited. High performance computing applications are especially sensitive to communication. Especially those that tightly communicate once parallelized. So without a good interconnect, which will be enabled by photonics, they just won't be adopted as much as they would have been otherwise.
It's my great pleasure and honor to introduce this morning's keynote speaker, a very good friend of mine, Dejan Milojicic, whose name, though he's given me many, many tutorials, I still can't get right. But I've known Dejan for many years. He has a very formidable background. If you read his resume, as I did last night again, you'll see how well organized his resume is. That's what I came away from your resume, because I didn't understand very much of the dozens and dozens and dozens of publications and tutorials and workshops, the titles of those that he's given. So Dejan is an outstanding volunteer with the Computer Society. I met him when he was editor-in-chief of something we call Computing Now, the Computer Society's web presence. He initiated that, grew it, matured it, to the point where he is today for the Computer Society, among other things. Among other things, he's the editor-in-chief, as I mentioned. He's also the lead in the Computer Society of a new construct that I talked about yesterday morning called Special Technical Communities. I asked him to head that up a couple of years ago, and he's taking this from, again, as he did with Computing Now, from nothing to a very important structure for the Computer Society and also for the IEEE. But anyway, this is not about that. This is about Dejan. This is about high-performance computing in the cloud, and I will now turn the podium over to Dejan.
Thank you, Sorel. Slightly better pronunciation of my name is Dejan Milojicic. And I work at Palo Alto. I work at HP Labs at the site in Palo Alto. There are many other sites. Also, to give you a little bit of context, what I'm working on before I embark on the topic of this presentation, there's a number of research portfolio in HP Labs. I happen to work in Intelligent Infrastructure Lab, which deals with high-performance computing, among other things, largely around computer architecture, system software, and things like that. And then I'm one of the few in Palo Alto who also works on cloud. The cloud-related portfolio is really being pursued in Bristol, in UK. So among you here, would you mind raising your arm if you are in the area of high-performance computing? Okay, I just want to calibrate what to talk. So it's really minority, and I presume the rest of you are working in the area of cloud, web services, cloud services. So for my own benefit and just to set the stage, I put what I think of, what comes to my mind about high-performance computing. I really like yesterday when the cloud computing team and Steve put up the revenue just to calibrate how much cloud computing will be. I think it was about 74 billion by 2015. To put it in the context of high-performance computing, today the revenue is around 10 billion. It is divided in supercomputers, divisional, departmental, workgroup servers, and then market is divided among servers, what you largely think about, but storage, another important aspect, then middleware, which a number of you who are probably in this area are working on, applications and services. There's a number of verticals. You'll be surprised how much. So high-performance computing are not just supercomputers. They deal with weather. As a matter of fact, having Sorel chairing this session, he helped me with arranging for the weather to be rain today. If you think why it's raining, it's so that you be here, not at the beach. And then there's a number of vendors, IBM, HP, Bull Cray, Fujitsu, and many, many others, both on server side, storage side, and then a number of ISVs. I just put a few: Adaptive Computing, Altair, Platform Computing. A number of them stem from long, long time ago. Then they all embarked on the grid computing bandwagon. Now they are just repackaging into cloud computing. So there's a lot of history there. What is cloud? Here are the numbers we were talking about: 72.9 billions. We were reading the same analyst report, Steve. It's divided. It's largely, primarily, if you ever thought about it, primarily most of the revenue is coming in the software as a service. It may not be obvious to everyone. It was pretty revealing to me to understand that. But then there are infrastructures for public cloud and private cloud. So it's pretty complex picture. And then there's a number of infrastructure as a service provider, a number of platform as a service, and it's not clear cut which are which. But there's even broader context if you think about it. I think it's important to understand the current state of the industry and the life, for that matter. We had Joe at the first day of this conference tweeting my slides all around the world. So that kind of things wasn't possible a few years ago. So, but let's take a broader perspective. So key mega trends: demographics, there's urbanization, increased middle class, aging population, health awareness. Really important. Cloud services are there in works for most of them. Globalization. I mean, if you just take a look who attends conference here, and that's, by the way, one of the strengths of IEEE, the broad coverage across all geographies. And then there are brands, markets, competition, partners, etc. Then social media that I already mentioned in the context of Joe and many others. And then there are different incarnations, both in terms of client interactions, referring, advertisements, etc. Then there's mobility. I mean, few people are, carrying laptops. I'm probably among the dinosaurs here. And it's in terms of product features, usage, communication, and then really important, sustainability. And I guess that's why we are here at Hawaii. So all of these really have impact. That's the context that we're thinking. So we're not just talking about there's a cloud, there's federation, there's this or that. It's for the purpose of these mega trends. And it's revealing how it evolved from mainframe, client server, internet, towards mobile, social. And then the really important aspects are these. Every 6 seconds there's close to 100,000 tweets. A majority of them comes from Joe. But many other aspects. How many apps are downloaded, how many pings, et cetera, et cetera. So these are things that really give the content. And then everyone is talking about the large scale. But there's not only scale in size, there's downscaling in time. So how quickly can you react? So if you look at the speed of business, how it's increasing, trading analytics, for example, 30 minutes in the past, 5 seconds today. If you don't get reply, Sorrel, when he calls me or sends me an SMS, he expects, within minutes, within seconds reply. Otherwise, he just calls me and says, "Dan, why aren't you replying?" And these are, but that's true for all businesses. Things are shorter and shorter, and that's kind of dynamics that are brought by cloud services. So now let's get into HPC in the cloud. First of all, it's growing, and I'll keep on coming on this. I'll try to beat that message over and over and over. But it's limited in scale to test and dev, and you'll see why. So some anecdotal evidence about Amazon, just for fun and advertisement. They built a supercomputer. They ranked 231st. They used 10 gig Ethernet, which is, by the way, one of the drawbacks. Another big message that I want to come across. And so they really delivered a supercomputer at the price of $0.60 per node per hour. If you look at real supercomputers, that's commodity. Now, that's one end. That's really the low end of HPC. At the high end, the U.S. Department of Energy, they are preparing for exascale. They've been doing it for years, and they are planning it slowly scaling up in the future, but still it's there. I think the current target is around 2020. It's the very high-end boundary, and what they are really planning are these numbers. So they're looking at the number of nodes up to 100,000. node concurrency up to 10,000 threads, although that's debatable. That's the at the moment debate between Intel, NVIDIA, and others who want to provide these processors. Interconnect bandwidth at 2 terabytes. And you can notice that they still want the same mean time to interruption of a day. Really hard to accomplish. And that's only the hardware. Then on top of it, you build everything else. So if you have any questions, by the way, feel free to ask at any point of time. Now, how do we divide this space? So exascale that I just mentioned, it's part of this elite supercomputing. Okay? It will never move to the cloud. It will just stay there. In the same way as you have mainframes in the banks, in the high-end banks, they're there, they're staying forever. But there are new startups. They cannot afford to buy mainframe. They cannot afford to buy time on the mainframe. So they're running on the in-house servers. Similarly, in the high-performance computing, that's one extreme where you have IBM Blue Waters, Blue Gene, which another Blue Gene just came to be the first. And then on the lower end, there's just Ethernet clusters. If you have embarrassingly parallel applications, you just run them there. What is interesting is this space in the middle, where you have this HP-specific, probably InfiniBand or some higher-end 10 gig or higher, and then some of the commodity hardware. So for this, everything in between, that's the battlefield to be fought for in the cloud. And that's the area that I was trying to address, and I'll be coming to that again. So let's ask us philosophical questions. Why clouds for HPC? And probably the hardcore HPC guys would say, just go away, okay? Clouds are no good. You can't do anything. Tell me what's the latency, tell me what's the bandwidth, go away. Well, that's not true for everyone. Those who just start a business, I think the gentleman yesterday at the panel said, get your degree and start up a new business as soon as you can. Well, these kinds of guys, they cannot afford. For them, the cloud is the answer. That's the, they're not going to get from venture capitalists any money for hardware. They just have to go into the cloud and get it. So these guys, especially those working in HPC, they will run it in the cloud, and they'll have to find the ways how to do it. That's one aspect. The other aspect is, even if they have money, by the time they get it, put it together, start it, they're already losing, these ideas. Someone else is picking it up. So it's the time to get it. So no startup, no maintenance cost. Time to solution, you just submit it there. You get that hardware, you just submit it. It's there. On the supercomputers, you submit it in a queue, and then it will get there if you have priority. Elastic resources, no risk on traditional things in the clouds. Power savings, because no matter how big supercomputer, no matter how big national lab, clouds will be bigger because they're serving the whole of the world. So you can presumably much better package everything and utilize it better. And then what came as a surprise to me, and it was actually reported by the Magellan report from Argonne National Lab, are the benefits of virtualization, which are a little bit different than general benefits of virtualization. Virtualization is beneficial in general for clouds because it improves utilization. You can better package, you can over-provision, and things like that. In HPC, the benefits of virtualization are primarily in flexibility and customization. On a supercomputer, you better not touch anything. Okay, you can't touch it. Well, in the cloud, you give your VM, you package it, you format it, you massage it, do whatever you want. So it is a cost-effective and timely solution. So the things are relatively rosy. How are clouds different than HP high-performance computing systems? Well, first of all, it's interconnect. They usually have GigE, at best 10 GigE, versus InfiniBand on high-performance computing. And the difference is huge. It's not just in the raw speed. It's also in drivers, in terms of how you copy. You go directly. You don't have to go through various layers of operating system and application. You have remote access. So the performance guarantees, latency, everything is dramatically better. Then virtualization versus tuned operating system. And we'll get to that. Virtualization has benefits, it has downsides, especially in terms of noise. So supercomputer and high-performance computing operating systems in general are very well tuned. No daemons, no nothing, no TLB faults, no page faults, really optimized so that, you know, the code can chunk, then you can copy, and again chunk until you're done. Then in cloud, you got to pay. You know, you got your credit card, but you got to pay on the spot. With supercomputers, it's grants, it's funny money, so there's not that understanding and mentality. You got VM instances in the cloud. I already mentioned in the supercomputer you have job submission system. Then software architecture, security, trust, governance, reliability, availability, etc., much different. And I'll touch on some, but not all of them. So things are still relatively rosy. I convinced you a little bit, not much. Some things are good, others are not. But let's focus on these aspects that are not as good. So clouds are optimized. You've seen that big picture with so many dots. That's the world for clouds. Social media and other stuff, web serving, web services, cloud services, but slow interconnect. So let's try to measure it. So we actually done it. I'll go and describe these platforms in a little bit more detail later. But for this time, think about public cloud, where Joe and his friends can go and run their high-performance computing jobs. Think about private cloud. Steve has his private cloud in IEEE, his testbed for running interoperability, and Dave. Think about just physical infrastructure, Open Cirrus, that's my cloud computing testbed. It's just a collection of physical workstation that we're using. And then think about two supercomputers. As you can see, and in that order, there's a performance. So for latency, you got very good performance on supercomputers, and then decreasing performance for other, with public cloud having the worst. And then the bandwidth is obviously opposite. But what is probably the worst aspect is this noise here. So these are the step numbers, and performance should be here, but you can see that on occasions performance go many times worse, and that's the big problem, unpredictability. And with high performance computing, you have so many threads that need to walk like military, you know, step by step. If one goes off, everyone goes off, and then it just accumulates and kills performance overall. So inferior network performance, virtualization overhead on network, and a lot of noise. And we just measured some. These are anecdotal evidences. Don't put too much into it than that. It's just anecdotal evidence. So we ran some experiments in eucalyptus, and this white space here in the middle, it's waiting time, so not utilizing the CPUs. And if you measure it here, you see the performance degradation on core 0 and core 1 only, and then both of them. So what happens is core 0 is running network virtualization and completely gets killed performance. Obviously, it's not optimized for high performance computing, but that's what you get in these cases. Now, let's think a little bit about economics, and I'll be getting to economics a few more times. The big aspect here is there's variable usage in time. Sometimes you use it, other times you are not, unless it's utilized completely. You can't justify your money. Then trading capital expenditure for operational expenditure. And then shift towards delivery model of software as a service. Especially important, and I'll get back to that many times as well. As a matter of fact, I have a whole section on that. So high-performance scientists, they don't really care about VMs. They don't really care about cloud, about servers, anything. What they care about is their topic. They want to know when it will rain outside. Not for swimming, but for other purposes. And you know, those who do genome sequencing, they care only about that. That's what they want to work. That's their passion. My passion is computer science. Being an engineer, their passion is their profession. So they don't really care about it. So if you can deliver to them HPC as a service, and their service specifically, that would be a huge win for them. So cloud is bringing that. Not quite, but bringing. Then there's cloud users' perspective. They can use cloud when their application fit the profile above, and then cloud providers' perspective. So cloud providers' perspective, first of all, you should understand that cloud business is a profitable business, but you have to have capital up front. And the more users you have, obviously, the better you can utilize your infrastructure. So for them, getting HPC in the cloud would be quite profitable, obviously. And then there's the opposite, reverse picture. Why not in the cloud? HPC systems today are already optimized. I mean, they are cranking it. especially the big labs. Smaller, a little bit less. So the notion of better utilization doesn't work well for HPC as it works for other systems. And then there's mismatch between HPC demands and cloud offerings. Performance sensitivity, we spoke about in a noise. And then CapEx, OpEx argument is less clear-cut for HPC users. It's there, but a little bit less clear-cut. Now, let me tell you, from my perspective, what are the three challenges in the cloud. The cost of energy. It's true for both cloud and HPC, and you've seen that even for exascale, they set up 20 megawatts as a limit, and Google's, Microsoft, others are fighting to get their PUE as close to 1 as possible. The second is explosion of data. I won't spend too much time on it, but I will a little bit. In the same way as it's true for social media, it's for HPC. All these genome sequencing guys and others, scientists, they are getting greedier and greedier. They want to, and they're more powerful, actually. So they can process more, and they get more data, and they want to accomplish more. And the completely new types of applications are coming that will require even more data. But commodity interconnects, absolutely the dominant factor there. Okay, so I'm just about to start presentation. The first part was motivation only. What I'll be talking today is I'll talk about evaluation of the HPC in the cloud. I'll put some attention on interconnects, virtualization, economics, and power just a little bit. A colleague of mine and I worked exactly on genome sequencing and how to deliver it as a service. And then I'll give you some thoughts of mine on financial services in the cloud, which is yet another compute demanding application. I'll talk a little bit about future trends which will impact high performance computing dramatically, and then I hopefully summarize. So let's first look at interconnect. It's really going to be about applications, but what it boils down, it's looking at how interconnect impacts applications. So some of that work was Bastion Paper Award at Open Cirrus Summit. There was a lot of past research. Most of it was focused on performance alone as a metric, mostly on small scale, up to a few tens of cores. It was largely focused on Amazon EC2 and message passing interface based. And most of them had pessimistic results, to be honest. So the research questions we wanted to answer were, what are the performance bottlenecks? Well, you know, Dan, are you crazy? You already told us 10 times it's interconnects. Well, okay, but we wanted to know how exactly are these interconnects impacting, and more importantly, how are they impacting on different hardware architectures and for different applications. So more thorough analysis thereof. And as a result, once we found out that, then we can answer the question, for that application, should I run it on a supercomputer or in the cloud? And what kind of cloud? Is it going to be just any cloud? Or do I have some HPC cluster in the cloud or something even better? Important aspect is not just performance, but how much am I going to pay for that? A big difference between HPC and cloud in general. For cloud, you pay. So here's the description of our experimental testbed. So we ran it on 2 supercomputers, Ranger and Tau, both running InfiniBand. Ranger is a little bit older, so it will have worse performance. Open Cirrus, which we used just as a physical cluster, so it had no virtualization. Then we ran on a private cloud. The big difference between private and public cloud is that on private cloud, we were able to be topology aware. We knew exactly where we run things so that we don't get just random VMs around a zone that is allocated, because you can only go today to the zone deep VM allocation. Hopefully, these kinds of interfaces will get exposed at minimum for the benefits of HPC. And then we also had a virtualization test bed, which had a number of different types of virtualization. So it had plain virtualization, it had thin virtualization, thin VMs, and then physical container, which is OS-based types of virtualization, and then it also ran on the physical machines. And we'll compare, so performance for all these 1, 2, 3, 4, 5 types of architectures, and then separately for virtualization. So this is not measured graph. This is just our hypothesis. Our hypothesis is that in the space of cost, latency, and performance ability, there are different surfaces. And we want to identify these surfaces for different applications. Different applications have their intrinsic patterns of behavior. And some of these will probably run better on supercomputers, other on clouds. And we want to understand that, especially in the dimension of cost. So you can see that supercomputer will be better here, and that for really high latency and powerful. And then cloud will be better here, where it will have, here where it has better, it has less cost. Another dimension was here on the y-axis you have slow down, and we did experiments for Eucalyptus versus Taub, which is supercomputer. And here we measure parallel efficiency. Parallel efficiency is defined as speed up divided by number of processors. So what we really wanted to identify this space and these applications here, which are really good candidates for the cloud. But we'll get back to that in a more exact manner. So here are the applications that we looked at. We looked at NAS parallel benchmarks. We only picked up 3. The others are similar. Then highly scalable molecular dynamics application, cosmology applications, Sweep 3D, Jacobi, and Queens. And so don't get frightened. Here are the performance. And there are some interesting observations here to make. You can see, for example, this is very indicative. You have very similar performance here. So if you have similar performance, no matter where you run it, you may as well run it in the cloud. In other cases, it behaves differently. In general, performance on the cloud, because we just took it vanilla, so it's not, we could have taken, for example, an Amazon cluster, optimized cluster, which would probably give us better performance, a better collocation. But if you just take vanilla public cloud, this is what you get. So it's probably among the best really here, where it scales up to 16 maybe, but for others it's pretty detrimental. And again, the message that I've given you, we use the VM of the size of 4 cores, so these 4 cores were collocated. As soon as it goes on another, possibly rack or God knows where, you get poor performance because you have to go across many boundaries. Another interesting thing is that Taub in general has better performance than Ranger because it's more modern supercomputer. But even but for larger scale, it beats other platforms other than so Ranger beats other platforms, even though other platforms have more superior performance. And the primary reason is InfiniBand, which isn't the best, but it's still better than Ethernet. So these kinds of things were interesting to find, and this is only performance aspect. We'll get to economics later. But this will enable us to then use this information and decide which application to run where. A negative side of this, as you already probably implied, is performance variability, which is really not good in high-performance computing other than on the supercomputers, where you can see that it's pretty good. For others, it's really bad, and especially in the public cloud. Private cloud is a little bit better, and Open Cirrus behind him. So let's look a little bit about the impact of virtualization and Affinity on the high-performance computing. So you have different types of virtualization techniques. In no virtualization, you just have user processes running. In plain VM, you have guest OS and host OS. And this typically leads to the poor performance because this host OS, there's some sequencing. I mean, there's virtualization of the networking interface, so you're paying penalty at this level. To improve performance, thin VMs go directly to the network interface, thereby getting this similar performance. But then there are issues at the scale. You can't do it for multiple applications, multiple VMs running on the system. And then container technology is different, whereby it has virtualization at the OS level, and that's more popular nowadays, but it has other drawbacks. So we've done experiments using, again, a subset of these applications and came up with assessment how these types of virtualizations contribute to the performance. And you can see that thin VM and containers can follow pretty faithfully the performance of the physical system where there's no virtualization, where plain VM has really the worst performance. Now let's look at the CPU affinity. Again, the consequence of virtualization. So no affinity means that any process can run on any core. So while process is waiting for I/O, it gets puts to sleep, and then when it gets up, gets woken, it can be run on any core, and that introduces obviously performance noise. And to improve that, you can specify affinity whereby each process runs on a specific core. Now that's good, that's well known from the past, but virtualization brings another layer. So another level where you can specify affinity. So you can introduce affinity from the process to the virtual CPU to VM, and then you can do the same thing. And only this will bring you full affinity. And what we've done is some experiments to show that. And so this is this very primitive application which does some random number and multiplication. And you can see there's a lot of variability here. And that's only for one of the few applications that has poor performance. If you introduce application level affinity only, you still have these problems, and only physical machine affinity will bring you better performance. And then looking at all applications that was ran on 12 CPUs, you can get only better performance if you can apply all these techniques. And then the same thing was repeated for the real application. The previous one was only a micro benchmark. So here you can see some of the anomalies here where this green is not expected, so we're still exploring that. So it's not that clear cut. Let's try to look at economics. We had some earlier work where we looked at traditional query. We've done this analysis 3 years ago. Everyone is doing this on a regular basis. So am I going to buy a computer or am I going to rent? Do I need to buy a car or am I going to rent a car or lease it? And we've done that actually maybe even more, maybe three to 4 years ago. Actually, the people from UIUC, they were deciding whether to buy equipment or not. So they got some funding, and then they looked at what would it take to run it on Amazon versus to just buy that equipment. And it is a function of utilization, obviously. The more you utilize, it's better to own. But the interesting thing is the break-even. And for computing, the break-even was, I think, somewhere about 12 months. And for storage, it was much less, about 5 months. So the providers really charge you premium for storage. And even for much larger utilizations than 20, you still get pretty good break-even. But that's traditional cloud, so anyone asks themselves. Let's revisit that question about why cloud for HPC. We were talking about CapEx versus OpEx argument, and then ability to take advantage of a large variety of different architectures. I mean, no matter how you are rich, you can't really buy all supercomputers there are, but if a cloud provider decides to offer them, it probably has much more muscle to do so. So if you remember that very busy graph with many applications, so we've done some exercise using that graph. So what we've done is, and it was not easy actually to come to this graph because we had typical apples versus oranges exercise. In a cloud, you know the price, but no provider will tell you the cost that they are paying. For high-performance computing, you know the cost, operational cost, but you don't know the price because it's usually the deal. So we actually found out both numbers. As HP, we know how much it costs, but they'll kill me, they'll execute me here on the spot if I say so. And then we knew how much the price was in one of the, actually Saarbrücken published some of the results. So we said rather than publicly stating it, let's use the range between 1 to 5. That's probably reasonable. So The cloud is cheaper because it's cheaper infrastructure. So let's just use it as a variable. So let's say it can be 5 times up to equal price. And then for these 3 applications only, we repeated experiments to see what is the ratio. This is logarithmic scale, don't forget. So for 1 core, it's much cheaper to run in the cloud, maybe 20, 30 times. And the break-even point is somewhere close to 30 for this Changa application. So if you scale up to over 30 applications, it's better to run in the cloud, cheaper, and then for larger, it's cheaper to run in the supercomputer. For others which are more communication intensive, it goes down all the way to around 8. So no news really here. You knew that for smaller configuration you will run it. What you didn't know is for which application at what break-even point you do that. When does it make sense to run where? So once you know that for application, once you characterize it either automatically or offline, you can then decide to run it in the cloud or in some cluster or other cluster or a supercomputer. There's a lot of related work. I would refer you to this US DOE Magellan's project where they decided not to go into the cloud, even though they recognize the benefit. But they are one extreme where they have supercomputers, well-oiled machinery used all the time. For others, it's a less clear cut. So we came up with these conclusions that if you can go with both, you are really best. If you have in-house supercomputer and go to the cloud whenever it's possible, it's better. And then we came up with understanding about this lightweight virtualization and the characterization of applications. So Nigel Cook himself developed most of the things. He did it as a student, actually. He's also HP fellow, just recently promoted, but he was also doing his Master of Science, and he developed this almost by himself. So here's the challenge that he was thinking of. Here's the scientist. That's where innovation happens. So in this human microbiome project, they sampled 242 healthy U.S. volunteers, collecting tissues from 15 body sites in men and 19 body sites in women, producing a number, tons of data, 3.5 terabytes of data. So here you go. You collect data. You get these 100 gigabytes per run. There's a number of solutions, such as Chimi, BioLinux, which are packaged software builds that you install on a laptop. Then there's integrated software and workflow platforms where you just go and run in the platform. There's a software as a service even further. And then various research clouds, of which Magellan was one. So Nefel approach was not just to give you that hardware infrastructure. They wanted Sorel to have full control of everything. Sometimes he forgets what experiments he did, so this will record all his experiments, it will record all his data, and then it will help Dave, who will have his federated cloud work with Sorel's cloud, repeat his experiments, because Sorel will give him access to these experiments so he can repeat. In other sciences, repeatability is really important. They don't even let you publish papers until some other team has reproduced same results using same data that you used. So repeatability is really important. So what happens there is not only that everything is orchestrated using those applications, scientific applications, but also commands are there, history, a lot of metadata, activities recorded, and then user management. And then there are a number of other value adds, such as everything is in the cloud, access is via browser, no rewriting of the software, it just as is, no programming languages, OS constraints, everything is independently developed, process is based on cloud publishing, so Sorel does something, changes, just publishes, and then Dave can see it. So important aspects and results contribution of this work is decoupling UI, orchestration from software publication, execution, and then cloud paradigm is there important, not virtualization. Here's how it looks like. So Sorel defines Chimi as this scientific application, and he says, well, if I'm going to run it on EC2, that is Amazon, I'm going to use this VM. If I'm running it on HP Cloud, I'm going to use this AMI. And then If Ron wants to run it on IBM, he can specify his VMs and et cetera, et cetera. And then he can just say run Chimie on HP Cloud, that's all, and use data from either Amazon or wherever. What happens is all this runs on a Google App Engine, so they used Platform as a Service for that. There's a queue of things that are submitted, and then it's all stored wherever. You can specify these repositories, and then you field off these requests either to Amazon or HP Cloud. But there's a lot of other things happening behind the scenes.